started. Thank you all for joining us today. So this is our second webinar of this series for this semester. And I'm Partha Mukherjee from the School of Mechanical Engineering at Purdue, if you don't know me. I also serve as the faculty advisor to this chapter. With that, it's my great pleasure to welcome our speaker of this week, Dr. Katie Jungjohann from NREL, National Renewable Energy Lab. She comes from the beautiful Smoky Mountain area. So also we have been discussing some collaboration over the last year or so with Dr. Jungjohann. And with that, let me welcome her to this forum and hand it over to Debanjali, who serves as the chapter president. And Debanjali is going to formally introduce our speaker. Thank you, Katie.
Thank you, Professor Mukherjee. So first, I got a MoChA today. And yeah, so let me give a quick introduction and I'll share my screen. Is my screen visible to you?
Yes.
Okay. Okay, so hello everyone. Welcome back to our webinar series. I'm Debanjali Chatterjee, a second-year PhD student at the Energy and Transport Sciences Lab and president of the ECS Purdue Student Chapter. I would first like to introduce our chapter advisory board. We are led by Professor Partha Mukherjee from the School of Mechanical Engineering at Purdue, who is our lead faculty advisor. Dr. Judy Jivarajan, Corporate Fellow and Vice President of Research at Underwriters Labs, is our Distinguished Industry Advisor. We also have Professor Rebecca Chase from the School of Mechanical Engineering and Professor Julia Laskin from the Department of Chemistry at Purdue as our co-faculty advisors. Let me present a quick overview of our chapter activities over the past year. In spring 2021, we conducted our signature webinar series on women in electrochemical sciences and engineering, comprising of a stellar lineup of women researchers from industry, national labs, and academia, both in the US and abroad. This series was exceptionally well received and appreciated in the scientific community. Inspired by its success, in fall 2021, we launched a webinar series on one of the hot topics in energy storage research, solid-state batteries and electrochemistry, inviting some of the leading academic and industry experts in this area. We are proud to announce that for our efforts in actively promoting scientific engagement and outreach on a global scale, we were awarded the 2021 Chapter of Excellence by the Electrochemical Society. The theme of this year's webinar series is Modeling, Characterization, and Analytics in Electrochemical Energy Systems, abbreviated as MoChA. Today's speaker is Dr. Katie Jungjohann from the National Renewable Energy Laboratory. Dr. Jungjohann joined NREL in 2021 after starting her career within the Department of Energy's Nanoscale Science Research Centers, including the Center for Integrated Nanotechnologies and the Center for Functional Nanomaterials. Her research began with liquid cell scanning and transmission electron microscopy of nanoparticle synthesis and catalytic nanoparticles. During her tenure at Sandia National Labs, she worked heavily on lithium metal anode characterization using in-situ electrochemical SEM and TEM and cryogenic electron microscopy methods. In addition, she led 2 development projects to advance in-situ SEM-TEM capabilities. Dr. Jungjohann supported research on an array of user projects that required in-situ SEM-TEM, electrical biasing, electrochemistry, heating in liquids, cryogenic, straining, and environmental TEM. She now supports her group's role in providing advanced analytical microscopy and imaging characterization to NREL and NREL's collaborators. Today, she will be speaking on Nanoscale Electrode Interfaces Revealed with Cryo-Electron Microscopy. Dr. Jungjohann, we look forward to your talk.
Thank you. Let me share my screen again. Thank you so much for having me, and please do ask questions. I learn a lot by understanding what doesn't make sense in these presentations, so I really look forward to hearing from the audience. So what I'm going to talk about today is a new area that Dr. Catherine Harrison and I broke into in the past couple of years. We were very close collaborators when I was at Sandia National Laboratories. And through learning about some new tools, we actually found a way to mill through coin cell batteries so that we could see the electrodes and the separator in cross section. And what you're seeing on the left is an slice and view image so that you have a 3D volume of the battery stack. And so the green is the copper current collectors, the blue is the lithium, and then we've removed everything else so that it's not getting in the way. But this helps us visualize the lithium electrodes in their topography and also look at dead lithium inside the batteries. And so here's some images of a coin cell and then the coin cell after milling with the laser plasma sieve, which I will talk about. And so that burn spot is from the laser. And then you have a bunch of batteries we've lined up here after characterization. And so I'll get into this. First, I wanted to start off with where I came from. So I grew up in Bend, Oregon, and I started my undergraduate University of Redlands in Southern California. Then I did 2 research projects. I did a summer at Lund University in Sweden, and then I also did a summer at UC Riverside. Then I went and worked or did graduate school at University of California, Davis, where I was in materials science and engineering. My project partially used a microscope called the Dynamic Transmission Electron Microscope that was at Lawrence Livermore National Laboratory, so I got to travel there. Then I did a postdoc at Brookhaven National Laboratory within the Center for Functional Nanomaterials. And so I was doing more of the liquid cell characterization that I'll talk about in a minute at this institution. And then I got a job at Sandia National Laboratories within the Center for Integrated Nanotechnologies, where I spent 8.5 years. And then this work is actually in collaboration with Thermo Fisher Scientific at their nanoport in Hillsboro, Oregon, and the University of Oregon. And then in October of 2021, I moved to NREL, where I hope to continue my career. I've moved into a group manager role, so now I do part of my time in management, but I still continue technical research. Okay, so if you're unfamiliar with transmission electron microscopy, here's an example. So on the left, we have, this was the environmental TEM that was at Sandia National Laboratories. This microscope set up so you can actually flow gases into the column around your sample and look at environmental characteristics like redox reactions. You can do hydrated vapor into the sample column and you can watch reactions as they occur. In STEM, so scanning transmission electron microscopy, you have all of your electrons focused down into a probe, which then you raster over your sample, and then you're collecting the signal of either high angle scattered electrons that you're seeing over here, which create a Z contrast image so that the contrast scales with the atomic number of the elements in your structure, or you can get inelastically and unscattered electrons with a bright field image, or collect that with a spectrometer to look at energy loss spectroscopy, which will give you information about the bonding in your structure and also the composition. And then we sometimes pair it with X-ray scattering up at the sample to look at heavier elements in your material. Okay, so in my graduate work, I looked at a lot of nanoparticle nucleation and growth. So here's an example of looking at lead sulfide nanoparticles grow under the electron beam. So this is in a liquid cell inside of the TEM, and we're imaging, which is breaking down the liquid in solution, which is then the electron beam is forming free electrons, which then will go and reduce the metal ions in solution and then grow these nanoparticles. I also was split between a molecular biology group, which we did some cryo-imaging and compared that to liquid cell imaging, where you can see here is very grainy image, but it's a ferritin in a molecule And we were able to image that in the liquid cell. And we can also image apoferritin, which is a the protein without the iron oxide core. So the top part has the iron oxide core and the bottom one is without that core. And then when I moved to Brookhaven National Lab, I continued some of this work looking at catalyst particles. This is also an image of assembly of these cad telluride. They look like Jack's, a toy for kids, but tetrapods, they assemble as you're drying out the liquid in solution. And so that was pretty exciting. And then another work was looking at galvanic replacement, where we were putting palladium on top of silver nanoparticles, which then the palladium would reduce by stealing the electrons away from the silver. And so you get this silver core that would be eaten away, and then a mixture of silver and palladium on the shell. So these are all things that you can do inside the microscope if you're unfamiliar with liquid cell transmission electron microscopy. But for our work today, I want to highlight my collaborators. So this work wouldn't have been done without meeting Dr. Renee Gannon and Dave Johnson at the University of Oregon. I was able to go there to collaborate before the group at Sandia had cryo-EM capabilities. And so they helped us do some initial characterization. And from Renee, I actually learned about this other tool that we used in the rest of our experiments, which then we collaborated with Dr. Stephen Randolph, and he was at Thermo Fisher Scientific. He's now moved on to Oak Ridge National Laboratories. And then, of course, all this work was done with Catherine Harrison right here and Laura Merrill, who is Catherine's postdoc, and she's now converted into staff at Sandia Labs, where they're really building and doing the electrochemical testing, and I've been doing all the characterization with Stephen Randolph and Renee Gannon. So our interest was in looking at lithium metal anodes because they can increase battery capacity by 10-fold, which is very important for long life portable electronics and also for electric vehicles that need a lot of power. If you're all familiar with batteries, I don't need to go to this in detail, but of course, instead of having this gravitic carbon anode, we would like to switch that out into lithium metal so that there's no host material, and we're just electroplating and stripping lithium on the anode side. And so a lot of our experiments, we're not actually looking at the cathode in the cell. We've been doing half cell experiments, and so we're just looking at the electrodeposition and stripping of lithium metal. To study this, we've been looking at 3 different configurations. We have our TEM liquid cell, which is an electrochemical platform that operates within the transmission electron microscope so that we can get nanoscale imaging of these processes. We've also done a lot with coin cells because they're easy to cycle and put together, and then to take the electrodes apart and image them separately. And then there's been work with pouch cells so that we can control the pressure instead of using just a spring in the coin cell, but we can use a load frame to then control that pressure. So how can we improve rechargeable batteries? Going with higher energy density, we would like to move from lithium ion into lithium metal. Of course, it's known as unsafe, and I'll get into that in a minute. But it's been projected to work very well for lithium sulfur batteries. And so getting into this higher energy density level is where the field would like to go. And so we've been focusing all our efforts into the lithium metal anode side. Why it doesn't work well is because it has an uncontrolled morphology. So lithium likes to form these high aspect ratio grains, which are not good because they will increase the interaction between the lithium metal and the electrolyte, which will then grow what's known as the solid electrolyte interface layer, which is this lighter green color on top of the blue. And then as you cycle, it continues to grow and develop. As you strip the lithium away, you can strip either from the tip or from the base. If you strip from the base, then you can be left with a lot of dead lithium that no longer contributes to your capacity inside your battery. And so we see lithium consumption both from dead lithium, but also from reaction with the electrolyte. And so we are trying to understand how to better control that lithium morphology. Now, I just want to bring up a couple different things that we can do. So a lot of electrochemical testing in the TEM has previously been done using open cell platform. So this is known as an STM TEM holder because there's a probe on this end here, which then can orient the sample to provide electrical contact. And this has been used for both solid and liquid electrolytes, where you can have your material set up on one side and then come in with either lithium metal with a solid electrolyte on top or with an ionic liquid electrolyte to contact a material, and then watch the material as it cycles. And this is actually looking at film on top of a nanowire during sodiation and desodiation, and seeing a buckling of that film due to the volume expansion in that material. And so I just want to show that there's other ways other than liquid cell imaging to look at these structures. Okay, so our group, we got very excited when we heard the results from PNNL at this new electrolyte, because they were showing a very different lithium morphology than what was known in carbonate electrolytes. And so here's showing the difference between cycling in 1 molar LiPF6 and propylene carbonate to what was shown here in 4 molar lithium FSI and dimethoxyethane. And so our group wanted to know what was the cause of this morphology difference. And so we put the electrolyte inside of our platform. When I was at the Center for Integrated Nanotechnologies, we had this electrochemical TEM discovery platform where you could pattern the electrodes to your defined layout and also composition, and then enclose it into with a lid, where then you're imaging through the center viewport, and then you fill the liquid through these side viewports, and then you seal it up with tape and epoxy. And I'll just say that there was 10 buried electrodes. So what was really nice about this platform is that it could run very low current experiments. So we were usually at around 2 to 20 picoamps, and then you could run multiple experiments with inside the same platform, so you had the same environment around the sample. And so we use this to look at that electrolyte. I also wanted to bring up that these electrodes, we can pattern heaters onto the platform. And so if you wanted to do temperature controlled experiments, they're very challenging, but they actually work really well. And this is just showing a resistance from this inside thermometer right here. Then you have a stovetop heater, and then this outer thermometer out here, and seeing the resistance to the temperature change shows that we can correlate that very well. And we also had a postdoc before, Dr. Andrew Lean here, who was able to confirm that with electron energy loss spectroscopy. So they're hard experiments, but they are possible. Okay, so getting back into this electrolyte, this is work with Dr. Katie Harrison, and what we found was that through cycling in this electrolyte, we weren't actually seeing a difference in the lithium morphology that we expected to see from the PNNL paper. And so we had very low clumpic efficiency, and the morphology was still high aspect ratio lithium grains, not these big, dense lithium grains that we were expecting to see. And so what we understood was that the layout of that TEM liquid cell was very different from what was being done in the coin cell, because there was no contact pressure on the electrode surface. And so we demonstrated that here with a cell in a coin cell with compression, where it had fairly good clumpic efficiency, and we're seeing these nice big lithium grains compared to a cell without compression, so just an electrode in a beaker, that you have this very open, mossy lithium morphology. And so the environment around the lithium makes a big difference on the resulting lithium morphology. And so this sparked us to go into a whole list of experiments in understanding what pressure on the lithium will impact the morphology, and if we can use this to tune the morphology to get the type of cycling and performance that we'd like to see out of lithium metal anodes. So in Katie Harrison's lab, she set up these pouch cells so that she had a lithium counter electrode on the bottom. Then she would enclose a separator with a working electrode, just a copper current collector on the top. And then she would seal that all inside of a pouch cell, filled the separator with electrolyte, and then sealed it up. So with these mirror finish platens, she could either use just weights to control the pressure, or she could use load frames that had feedback control so that they would keep the pressure consistent as the lithium plated and stripped, because you can imagine there's a lot of volume change as you plate and strip the lithium inside the cell. Okay, this is what was found. So for low current, the effects of pressure going from 0 kilopascals, 10, 100, 1,000, and 10,000, you can see that there's actually an improvement in the capacity as you're going from 0 up to 1,000 kPa. But then as you get to 10,000, there's a bit too much pressure where we're thinking that that's causing an increased overpotential and some transport issues, likely because the separator in between the electrodes is being compressed too much, and that the pores is restricting the electrolyte from moving between the electrodes. And so we see that there is kind of an optimal range for getting better performance of the lithium for plating and stripping. Now, of course, if you're comparing just the cycle number and the ways that these electrodes fail, you can see that some of them at no pressure over here would short very quickly, and then some would run out of accessible lithium, whereas at higher pressure, it would just run out of accessible lithium after some time. And so we knew that the failure mechanisms were a bit different between the low pressure and the higher pressure case. Now, we had a hard time imaging lithium. This is lithium if you're imaging it inside of a TEM under more normal conditions. So a beam current of 0.5 nanoamps over several minutes. You can see here that the lithium actually just pretty much sublimates. It disappears because it's being broken down by the electron beam. And so in 2017, I was very excited to see this paper come out by Yusui's group at Stanford, where they showed that you could electroplate lithium onto a copper grid and then plunge it in liquid nitrogen, load it into a Cryo-TEM holder, which is just a liquid nitrogen dewar that has a metal rod going down the tip of the holder to keep it cooled during imaging in the microscope. And so they use this to then image lithium metal after cycling and look at SEI character. The other paper that was very inspiring to our group was this one from Lena Korkudis and Michael Zachman from the Cornell, where they were able to set up a focused ion beam where they had a cryo stage to hold the sample, and then they also had a cryo lift out needle so that the sample stayed cool so that they could lift out an electrode in contact with an electrolyte. And so you're seeing here a lithium dendrite in contact with an electrolyte, and then they could image this inside the stem with eels to then get maps of the carbon, oxygen, fluorine peaks to better understand the SEI in contact with the lithium and the types of lithium dendrites that would form after electroplating. We also were able to do some more high resolution imaging using these cryo holders and a direct electron camera. And so we were able to do a very low dose of the electron beam over the sample. And then you could see that these lines just highlight some of the lattice in the lithium metal that was imaged under the electron beam. And so the tools really matter for getting good characterization out of these battery electrodes. And so this is why doing it at certain sites makes a big difference. Okay, so when I was at CINT, we invested in a suite of tools for cryo-electron microscopy. So there's a VitraBot that will plunge the sample into liquid ethane to freeze it very quickly. This is important for anything that has an aqueous environment so that you're not getting ice crystals or an abundance of ice crystals during imaging. Then there's a SIOS cryofib. It has a cryo stage that can be installed or taken out. And it does have a cryo lift out needle. So that's all cooled together. And then there's tools for transferring the sample from a glove box into either a sputter deposition or into the fib or into this platform, which then you can load and move the samples around under liquid nitrogen. It's pretty much just a liquid nitrogen bath. And then you can load the sample into a cryo holder to go into a cryo TEM, which is a cold box that sits around the sample so that you have more time to do cryo imaging, or if you need to do tomography where it's stable at that low temperature, because a lot of the cryo holders will cool and be stable for a certain amount of time, and then they'll start to heat up again, and you need to continuously cool and restabilize them. And so it's hard to get very long collection times of your data. Okay, so now moving into the study of using these cryo tools to understand how pressure impacts the electrodes. These are images of cross section. So what we did was we had Katie Harrison and Laura had the electrodes in the coin cell. Those were taken in part inside of a glove box, transfer over to our lab, and then we would load them into the inert transfer system to go into the cryofib. And so these are just little pieces of electrode that were cut out from the coin cell stack. And so we had pulled off a separator to do this type of imaging. So what you're seeing is in low current conditions with low pressure, you have a very open network of lithium. The lithium is the dark contrast here. There's some redeposited material that's very bright here. And there's a very thin layer of SEI that we can see on top of the lithium. It's tens of nanometers thick. And so there's not a lot of contrast here. We could zoom in and get some better images of it, but we couldn't get any elemental analysis, so we didn't spend a lot of time on that. But you can see both from the top down images of these electrodes, the porosity of the lithium metal goes down with increased pressure. You can also see that in the cross-sectional imaging here. And then we have thickness that we measured from these electrodes depending on the pressure. So at 0 kPa, it was almost 90 microns thick, whereas at 10,000, it got all the way down to 17 microns thick. And you can see there's very, very small pores in here, and it's mostly just a very dense lithium deposits in very large grains. So how that changes at high current was quite interesting, because we expected to see a significant difference with pressure for a high current. So previously we were at 0.5 milliamps per centimeter squared. This is at 4 milliamps per centimeter squared. Now you're seeing that there's almost identical lithium morphology. The height of the deposits did change with difference in pressure, but the lithium grains are still very thin, small, and more filament type of structure. To me, it looks a bit like spaghetti because it's all mixed together and it has a lot of these pores in here intermixed. And so what we understand is for high current density, that there's really some transport issues. And so the lithium just deposits everywhere it can instead of forming those nice big lithium grains that we were seeing at the low current. And so this pressure did not solve the issue for the lithium morphology under high current conditions. And you can see this too in the electrochemistry. So going from 0 up to 1 megapascal, the electrochemistry, it got a little bit better, but there's still a lot of variability and a lot of scattering. You can see in the Coulombic efficiency where sometimes we were measuring over 100% in Coulombic efficiency. And that's because we believe things can break and reconnect, and also that there's forming electronic charges through the separator in the material. And we'll talk about that in a minute here. Okay, so at low pressure, we really wanted to understand what happens after that first cycle. So all the images you were seeing before was the first deposit of lithium. Now this is after 50 cycles, so plating and stripping. So this is the 51st plating step on the working electrode. And what you're seeing here for the low current imaging, low current conditions, is that there's a lot of electrolyte that's filling in the low pressure electrode. And so due to all of the porosity, we weren't able to dry out that electrode enough to get nice clean images. And so a lot of this is electrolyte that's was heating up under the electron beam as we were imaging it. Under higher pressure, you could see that there were some nice big lithium grains in here, but there was a lot of reacted material that was SEI components. At 100 kPa, again, it was really hard to see large lithium deposits. There's some lower down, but because of all the cycling, these electrodes get very thick. And so it was getting to a point where we couldn't use the gallium fib to mill through the electrode to get all the way down to the current collector. And so we couldn't do those measurements of knowing how thick the electrode was after cycling. And then at the 1000 kPa, you can see, again, there's some lithium metal down here, but a lot of this is reacted material, reacted with the electrolyte to form SEI. What I found very interesting, and you guys already heard the talk from Steve Harris, but I love this paper that he did that shows that the amount of variation in performance with identical coin cells. And so I think that, you know, we really wanted to understand why the lithium was depositing in different morphology, but it was hard to get a good enough picture using these techniques because we had such a small sampling size. And what we really needed was to see the electrodes and the whole battery stack as they exist together so that we could understand if it's failing, why was it failing, and what was causing that. And so our collaboration with Thermo Fisher Scientific and University of Oregon led us to this instrument, which is a femtosecond laser that's attached to the side of a plasma focused ion beam. So you have the laser coming in here at a 30-degree angle from the side. The plasma fib is on the other side of the instrument. And then from the top down, you have the SEM beam to take your images. And so all these are actually oblique cross sections through the sample. So they're not exactly perpendicular to the battery stack, but we were at a good enough angle where we could really see all the different layers with clarity. And what was impressive about the femtosecond laser is that it mills 15,000 times faster than the gallium fib that we were using in the previous work. And so this was enabled us to cut through about 1 millimeter by 1 millimeter of material and 1 millimeter down so that we could get a complete cross-section view of the entire battery stack. And that's what you're seeing on the side here. So here's a coin cell mounted inside the cryo stage in the laser plasma fib. Here's the section after it's been milled out. So this is going through the cap, the stainless steel cap of the coin cell. That's 250 microns thick. And then you can see the battery stack down here. Then using imaging in the SEM and EDS mapping, we were able to identify the different layers of the battery stack. So you had the copper, this is electrodeposited lithium, which is very dark, intermixed with some electrolyte and SEI. Then we had two CellGuard 2325 separators, which were polyethylene and polypropylene, which we could see the different layers of the polymer in that separator. And then below we had electrolyte that would fill in the counter electrode of the lithium metal. And this was that large deposit with a copper electrode below. So this is just showing how the tool fits into the other suite of tools that exist for understanding batteries. So everything we were doing before was with a gallium ion fib. So we were really cutting up to about 100 microns and getting features down, to 500 nanometers. But when we were trying to use micro CT, we couldn't get the resolution that we needed. You can get down to about 700 nanometers, but we weren't able to easily distinguish the different parts of the battery, especially after cycling. It becomes very messy. And so we needed a tool that was able to bridge this gap between 1 millimeter down to below a micron so that we could see those intimate features of the electrodes, but we could also put that in perspective for the coin cell as a whole. Okay, so here's an example of what it looks like. So we used a wedge to get a higher angle of the electrode stack inside the plasma fib. Then we have a shutter that comes down to protect the SEM column from the laser because there's a lot of ablation that occurs, and so that shields the SEM column from that. And then we did try pouch cells, but unfortunately the thermal mass of the pouch cell did not stay cool. And so for liquid electrolytes, that's not a very good plan because they heat up very quickly. So this stage where most of our imaging was done, the stage was held about negative 110 degrees C. And so some of the newer stages can go closer to liquid nitrogen temperature, but this is where we were at here. We also learned that we didn't want to have the counter electrode on the top side of the coin cell because we started out with a 750 micron lithium counter electrode, and that was a bit too thick. So this is imaging the all the way a millimeter down, and then at the very bottom you could see the battery stack down there. So what we did was we inverted everything and we went to a thinner counter electrode for the lithium metal. And so instead, this is a 50 micron lithium counter electrode. Okay, so our first paper was just showing the ability of this tool. And what we did was we compared what happens to a coin cell, and this is 2.8 molar lithium FSI and DME with 2 CellGuard 2325 separators, cycled at a fairly high rate. And so the pristine cell, the separator we false colored to be this blue, and then the lithium's in red, and then the copper for the current collector. With the first lithium deposit, you can see the lithium shows up fairly porous and intermixed with some electrolyte and SEI. Then as you strip that away, some of the lithium was left over, and the lithium that redeposited on your counter electrode was very open and porous. Cycling 10 more times, you can see that there's actually a lot of SEI that has built up and SEI that has infiltrated into the separator with time. And then this 51st deposit really shows that these processes are stochastic. So all of these examples are different batteries, and this battery in this location, it did have a stable separator and didn't have infiltration of the SEI into the separator, but we found that with extended cycling, that was very common. I also point arrows here for the cracks that formed in the SEI as you plate and strip the lithium. And then under failure, you see here at 101st lithium deposition cycles, that there is some lithium metal that deposited within the separator. And so this is just showing a predominant failure mechanism, at least under these conditions. This is just showing that when we were trying to do the gallium ion fib of these thick deposits in the coin cell, it became impossible to remove the separator from the electrodes because they really become intermixed and intertwined eventually, and there's a lot of SEI product and also lithium metal that can form inside of the separator with extended cycling. Okay, so the way that we looked at pressure using this tool was to cycle the electrodes under a pouch cell, and then to take the pouch cell apart, cut it up, and then to load that into a coin cell, which then we loaded into the cryo stage of the laser plasma fib and did imaging there. So what you can see here is with pressure, for low pressure at the electrodes, there's almost no lithium left over after 51 cycles. And as you go to higher pressure, there's more lithium left over, but it's really dispersed throughout the cell, and it very quickly is removed from the counter electrode at the bottom. But we see a lot of it deposit within the separator or between the separator layers. And commonly we saw the separator layers fall apart after cycling. This one is just showing the electrode deposition of lithium within the separator and how common that was, and how we usually actually saw a lot of interconnected networks of larger lithium grains within the separator. But it is a problem with these separator combination with that electrolyte. The other thing that we did was we looked at a variety of different electrolytes and tried to understand failure from this system level scale. And so in comparison of 1 molar lithium PF6 in EC-DEC compared to 4 molar lithium FSI and DME compared to a mixture of 2 molar lithium FSI with 1 molar lithium TFSI and DOL DME, you can see that there's a variation in the cycled structure. So this is just the first deposit of lithium from the counter electrode to the working electrode. In the carbonate electrolyte, you can see that there's very small lithium deposits that formed. They're very spread out, and a lot of SEI has formed. This is indicative of a gas bubble that has formed on the counter electrode, because this silver material here is actually the steel that redeposited, and so that's showing a gap that formed in the that was in the structure, and then where we were imaging that there was a big hole there, and that's why the steel filled it in. With the 4 molar lithium FSI and DME, it actually had the least reaction with the electrolyte, and so you're seeing the least amount of SEI product, and it's the thinnest from the stack level. But there are large pits that formed in the counter electrode during the lithium plating, and the lithium grains are a bit larger, but there's still a lot of porosity there. In this concentrated bisalt electrolyte, you can see there's a lot of pitting in the counter electrode from the lithium, and there's not a lot of large lithium grains that formed on the working electrode. Okay, if we go to high rate, so that was done at the low rate of 0.47 milliamps per centimeter squared, at a high rate of 1.88 milliamps per centimeter squared. What you can see now is a lot of similar characteristics. We're seeing, again, there is some gas that had formed in the EC-DEC case, and there's some reaction with the separator in a form of a layer in between the separator layers. The 4 molar lithium FSI and DME was more stable, but very small lithium deposits, and again, not a very good network for this, but less of that pitting behavior was observed in the concentrated bisalt electrolyte. Okay, and now comparing this at long extended cycling, so 101st lithium deposit, you can see that in the carbonate electrolyte, all the lithium has been consumed and has been converted into SEI. There's large gas bubbles, large cracks in the SEI, and pretty much everything's mostly disconnected from each other. In the 4 molar lithium FSI and DME, you can see that there's some, there's still capacity left, there's still ability to plate and strip, but there's a lot of SEI that's formed, and also in the concentrated bisalt solution, it looks fairly similar, but less reactive to the separator than we saw with the DME situation. At high current, the behavior was not as good as low current. There was still some residual lithium in the carbonate electrolyte, but it looks like it's fairly disconnected from the rest of the cell, because we see these cracks and these pits that have formed around the lithium inventory at the bottom, and so we don't really think that that's probably active lithium, that it's been restricted from access, and the electrolyte's been mostly consumed, so there's no longer transport in that cell. In the 4 molar lithium SI and DME, you can see again there's a lot of lithium inventory left, but there's not a lot of lithium depositing on the working electrode. And then for the concentrated bisalt, under these conditions, there was just a lot of reaction with the electrolyte, and so it's consumed a lot of the lithium and formed SEI. Okay, last thing I want to say is that we can use this, the femtosecond laser, to cross-section mill and image, which then we can create these 3D volumes, and we can understand the topography of the lithium and look at dead lithium as it exists. Because some questions you have when you look at a cut face is, okay, well, is it still connected even though there's a lithium grain that's way down closer to the separator, maybe there's still a network that connects it up. And so from this slice and view imaging, we're actually able to get evidence of if the lithium's dead and disconnected or if it has pathways. Of course, that only goes down to a certain scale, but hopefully in the future, as this technique becomes more explored, there'll be a higher resolution type of imaging and characterization here. Right now, the femtosecond laser cuts in about 10 micron slices, and so it's hard to go below that in the cut faces. Okay, so in conclusion, what we found for the effects of pressure on liquid lithium cycling are that they can be overlooked, and it's very significant for understanding failure and understanding the cell-to-cell repeatability and also the Coulombic efficiency relative to your lithium inventory. So we understand that too much pressure will cause transport problems, even at low current density, but the high current density obviously is always restricted. The pressure for high current density did impact the lithium morphology, and the pressure did show to slow the lithium inventory loss, but there's still a lot of work that needs to be done there to stabilize that lithium morphology. The cryo femtosecond laser plasma fib was able to image intact coin cell batteries without disassembly, and so that really helped us understand what those electrode thicknesses actually are, because you can imagine if you were pulling the separator off of the counter electrode or the working electrode, then a lot of that SEI might get pulled off with the separator, and so it's hard to do that characterization individually. And so we could use this technique to quantify the lithium inventory, the lithium morphology, cracking in the SEI layer, and also the SEI thickness within the cell. And we found that under high rate cycling, these separators are easily damaged and destroyed, and so they're not very compatible for lithium metal anodes, and that's an area of development. So with that, I want to thank you for your attention, and I'm very happy to take any questions that anyone has.